Hello everyone, this is Dr. P. Rajkumar, Assistant Professor, Department of Mechanical Engineering, KLEF. Welcome to Machine Design course. The topic for today's discussion is design of flanged coupling. So the aim of the present session is to make you to familiar the design of flanged couplings. That means how to design a flanged coupling in order to avoid the failure of that component. So what are the stresses will be developed inside the flanged coupling and what are the forces acting on it, what are the standard dimensions we have to consider while designing a flanged coupling. Everything will be discussed as part of this session. So at the end of this session you will be knowing how to design a flanged coupling for a particular application. So let's start the session. Like the flange couplings. So you have seen already the flanged couplings. Here these are the two shafts and these shafts, aligned shafts, are connected using some flanges. Left side one thing and right side another. These two flanges are connected. These two flanges are connected using bolts and nuts. So majorly the flanged coupling is used to connect to aligned shafts. And coming to the classification of the flanged coupling, they have three classifications. First one is the unprotected type flange coupling, second one is the protected type flange coupling, third one is the marine type flange coupling. The first one is the unprotected type flange coupling. Here if you see, the bolts and nuts are used to connect both the flanges, but these are not covered. That means during the operation they may cause the injury to the workman who is working there. So these kind of couplings we will call unprotected. Whereas if you see here, these nuts and bolts are not on the open side, they are inside. That means there is some housing is there. So these kind of housing you can find in the protected type flange coupling, and these are like marine type. There is no extrusions, completely it is inside. It is like integral part here with the flanges itself. So these are the three different flange couplings. First one is the unprotected type flange coupling, second one is the protected type flange coupling, third one is the marine type flange coupling. So now let's see how to design what are the standard dimensions of each type. So coming to the first one is the flange coupling, that is nothing but unprotected type flange coupling. So here if you see on the right hand side, what are the major components here? First one is the shaft, next one is the key, another one is the hub, then flanges, then your bolts and nuts. So whenever we are doing the design for flange coupling, we have to ensure the safer design for all these members, such as we have to ensure the safer values were taken for the designing of the shafts, safer values were taken for the designing of the keys, then your flange, then your bolts and nuts. All the things we have to consider in the design of unprotected type flange couplings. So coming to the standard dimensions, that first one is the D is the inner diameter of the shaft or the inner diameter of the hub. You can say the small d is the diameter of the shaft, and capital D, it is nothing but it is the 2 times of your small diameter. This is the hub diameter, capital D, and length of the hub, capital L, is equal to nothing but 1.5 plus 1.5, that means 3 times D. That is a pitch circle diameter of your bolts, because where is the D1? D1 is here. So this is a pitch circle diameter and this is equal to 3 times of D, and length of the hub is equal to nothing but it is 1.5 times of D, and outside diameter of the flange, that means D2. This is the outside diameter of the flange. This diameter is standard value 4 times of D, that means 4 times of diameter of the shaft. And now coming to the TF. TF is nothing but the thickness of the flange. This is called, the standard value for thickness of the flange is 0.5 times of the diameter. So now how many number of bolts we have to take in, how many number of nuts we have to take in, everything will be depending on the diameter of your shaft. For a diameter of the shaft up to 40 mm we have to use 3 bolts. For a diameter of 100 mm we can use 4. For 180 mm we have to use 6 mm. So these are the standard values. And during the designing of this unprotected type flange coupling, you have to consider all these values, all these standard values. Now coming to the protected type, the only difference between the unprotected and protected is all the values will be similar to unprotected type flange coupling except this TP value. TP is nothing but the thickness of the protected. Okay, TP is nothing but protective circumferential flange. What is the value, thickness of that circumferential flange we will take. That value is the standard value and that is equal to 0.25 times of the diameter of the shaft. So by incorporating this TP value, by considering all unprotected value, we can do the designing of protected type flange coupling. So now coming to the design of flange coupling, that is in general what are the factors we have to take. So as I discussed earlier, D is nothing but it is the diameter of the shaft, capital D is nothing but outer diameter of the hub, and small d1 is nothing but nominal or outside diameter of the bolt. This you can see the what is the d1, capital D, what is the d2, everything here in the diagram. Capital D1 is nothing but the nominal diameter or the outside diameter of the bolt. Next one is the small n is the number of bolts. Here you can see what is the number of bolts that we are using in this flange coupling design, and TF is nothing but the thickness of the flange. So tau S, tau B and tau K are the different shear stress values. S stands for shaft, B stands for bolt, K stands for key. So these are the tau S, tau B and tau K are the three different shear stress values for those members. Now tau C is nothing but allowable shear stress value for the flanged material. C is nothing but coupling. So what is the material we are using? Cast iron. C stands for the cast iron. Sigma CB and sigma CK stands for the crushing stress for bolt, crushing stress for the key material. So these are the nomenclature and these are the standard dimensions that we have to consider during the designing of the flange coupling. So now let's see one example how to design a flange coupling for different applications. So this is the exploded view of the flanged coupling. You can see here the flanged coupling is used to connect two shafts which are aligned, and this is the key. This is called keyway. So this is the saddle. This is the sunk key, like square. This is the sunk key. It is like a square cross section or rectangular cross section we can take here. So this is the rectangular one. So this is the key used to connect your keys and the rotating members. So this is the keyway and the flanges here and the bolts. These are the different parts that involved in the designing of the flanged coupling. So now let's discuss each design criteria, because if any one of the components fails, then entire flange coupling will be failed. It can be treated as the failure of the component. So in order to avoid all those things, we have to ensure the proper designing of its individual parts. That means designing of the shaft, designing of the keys, designing of the bolts and nut, designing of the flange, everything we have to take care. So the design of the hub, the first one is the design of the hub. So if the hub are nothing but inside diameter of the shaft, if the hub is subjected to the your shear stress, then since we are treating hub is the internal diameter of the shaft, then the twisting moment can be written like twisting moment is equal to pi by 16 into tau into d power 4 minus small d power 4 by capital D. So using this equation and by substituting capital D is equal to 2d and small d values will be like that. By substituting all these values, you can get the small d diameter of the shaft using this equation. The length of the hub and other capital D values, everything is mentioned here. Now coming to the design for keys, as I already told you and as already we discussed, the key will be subjected to shear stress as well as the crushing stress. So we have to ensure the safer design of the key in both the conditions. Then only we can claim the design of for key is safe. Otherwise assume you have designed a key to withstand only twisting moment, but it is failure in the crushing. So then it will cause the failure of the entire component. That's why while designing a machine component, we have to ensure for all its failure criteria, it should satisfy the design conditions. So here also the key should satisfy the design conditions or the failure conditions for the your both shearing stress as well as the crushing stress. Now coming to the design for flange. So here the flange at the junction of the hub, it also will be under shear stress while transmitting the torque. So the twisting moment can be written using this equation, and finally we can reduce the equation is equal to twisting moment is equal to pi by 2 d square into tau c into Tf, thickness of the flange, shear stress of the coupling, diameter of the hub, and then twisting moment. By substituting all the values you will get the capital D value, and from that equation you can calculate the small d, diameter of the shaft. This for another equation, that is design of the bolts. If you see here, again I told you the bolts which will be subject to the twisting as well as the your shear stress as well as your crushing one. So if you see here the shear load on each bolt according to your crushing one. So the area will be pi by 4 d square into sigma 1. Then the total load that is acting on the bolts is, first you have to consider how many number of bolts are there. N is the number of bolts, then the load acting on the each individual bolt, pi by 4 d1 square into tau b. So this is the equations majorly used to calculate the transmission or twisting moment or torque of the shafts. So similarly this is the equation, this is the area is N number of bolts d1 into Tf. So this is the area of cross section which is used to calculate the crushing stress of that engineering stress. So during the problem solving also we have to consider all these factors for all four conditions. Now let us discuss one problem on the design of a protective type flange coupling. So here if you see, they are asking design a protective type flange coupling for shaft transmitting 15 kilowatt at 200 rpm. Now they are asking assume suitable material for shaft, bolt and key, and the maximum torque they have given it is 25% extra than the mean value. So in order to design a protective type flange coupling, what is the first thing we have to do? They told assume the suitable material for the shaft keys and the bolts. So from the design data book, just now whatever I have shown, from the design data book page number 1.10 we can say that C45 carbon 45 materials for the bolt, construction of the bolt, and C50 material for the shaft and key, and for 1.12 conditions. From page number this 1.12, and what is the type of conditions of that shaft, we can have to know the yield strength value as well as your crushing value. So the yield strength value is given 380 MPa for these conditions. So now assume the factor of safety during the designing of this flange coupling is 2.5. So now by substituting these values we will get the allowable values. So for sunk for shaft and keys the tau max is equal to tau ys, that means shear load in shearing, shear loading in shearing tau ys by FOS. It is here the factor of safety is nothing but 2.5 here. So by substituting its value here 460 in this equation you will get the tau max as 92 MPa. Similarly for bolts you will get the 76. Crushing, again crushing stress by substituting the values you are getting 152 MPa, and here key also you are getting the value as 184. Here if you see the maximum shear stress developed inside the shaft is exactly half of the crushing stress, because the crushing stress is 184 MPa whereas this tau max is only 92 MPa. So this is the one parameter you have to consider, and these values were we have taken from the standard design data book. Now in order to solve that one, the first one is you have to design it for a hub design. So what is that value you have to consider? The T mean value we are taking, and since they have told the maximum torque is 25% is greater than the full mean torque, that means T max is equal to 1.25 times of T mean, that we can consider tau max value. Once the tau max we know pi by 16 into tau into d cube. So this is the equation we have to use to calculate the diameter. If you submit all the given values you can calculate the d value. So diameter of the shaft, length of the shaft, then these values everything If you substitute, then you will get the crushing stress. So here we have calculated shear stress, here we have calculated the stress for the coupling. So if these values are well within the allowable limit, then we can say the design for hub is safe. And now similarly for the design of keys, design for keys. So you have to take the standard dimensions like width, thickness, the length of the key, and after that then you have to calculate the twisting moment from the when the key is subjected to the your shear loads, and similarly you have to bring the twisting moment or torque moment from the crushing loads. So by substituting all the values you will get the designs of for keys, because design of the keys is always involves this diameter. Third one is the design for flange. I already told you these flanges are used to connect the two aligned shafts. So in order to design for flange, first we have to consider the flange thickness. Generally this value is taken as 0.5 times of diameter. So since it is used to transmit the torque, then we have to use this equation. So substitute the T max is equal to pi by 2 d square into tau c into Tf. So by substituting all the values here, you will get the allowable tau c value. Whether the developed tau c is less than allowable or not, you have to cross check. It should be less than the developed allowable value. Then only that component will not be subjected to any failure. Now similarly for the design of the bolts. So N is nothing but number of bolts, capital D is nothing but pitch circle diameter of the bolt, T max is nothing but the twisting moment. So by substituting all the values, in this given equation, you can come to know the diameter of the your shaft. So that's how whenever we are designing a protective type flange coupling, we have to ensure our design is safe for all the components, like design for hub, design for key, design for flange, then design for bolts. Whenever all these 4 criteria satisfies, then only we can say the design for particular component completed. So these are the different references and textbooks for further learning. Thank you.